The sun hides a restless engine beneath its bright face. Inside, boiling gas and tangled fields stir, shaping the storms we see. Beneath the glowing surface lies a sphere of gas so dense it feels like a thick syrup. The inner core burns at temperatures that would melt steel, but pressure holds the reactions in a steady rhythm. Energy born there takes a long, slow climb outward, first through a radiative shell where photons bounce like pinballs. I note the time it takes, millions of years, to diffuse that way, a patience the sun cannot afford. At roughly 70% of the solar radius, the material changes character. The plasma becomes less opaque, allowing heat to rise in bulk. This is the convection zone, a churn of hot bubbles that swell, drift upward, shed heat, then sink again like a pot of thick soup. The motion is not smooth. It cracks, splinters, and creates eddies that ripple through the entire layer. I can almost hear the faint hiss of plasma slipping past magnetic lines, a soundless friction that still leaves a trace in the magnetic field. The sun does not spin like a solid ball. Its equator completes a turn in about 27 days, while the poles lag behind, taking 31 days. This differential rotation stretches and twists any magnetic thread caught in the flow. I find it hard to picture a line of invisible force being pulled apart by a giant, invisible hand, yet the math shows it clearly. The shearing motion stores energy in the field, much as a twisted rubber band stores tension. When conductive plasma moves through an existing magnetic field, it induces electric currents. Those currents, in turn, generate new magnetic field components. This feedback loop, known as the dynamo process, keeps the sun's magnetism alive. In the lab, we can reproduce a tiny version with liquid metal in a rotating cylinder. The sun does it on a scale that dwarfs any experiment. I write down the key point. Motion plus conductivity equals magnetic growth, and the sun's relentless convection supplies both. Plasma, unlike ordinary gas, carries electric charge. Its particles respond to magnetic forces, and the field lines become frozen into the moving fluid. As the plasma swirls, it drags the field with it, bending and folding the lines into complex shapes. I sometimes imagine the field as a tangled skein of thread, each strand pulled by the surrounding flow. The tension in those threads can become extreme, but the plasma's pressure holds them together, preventing an immediate snap. Sometimes a bundle of magnetic field, a flux tube, gathers enough strength to push through the convective layer. When it reaches the surface, the tube opens a window in the otherwise uniform photosphere. The spot where it emerges appears darker because the strong field suppresses the upward flow of hot plasma. Less heat reaches the surface there, so the region cools by a few hundred degrees. We call those patches sunspots. Their dark centers, called umbra, are surrounded by a lighter halo, the penumbra, where the field lines spread out like a fan. Sunspots are not permanent. They drift, grow, and decay over days to weeks. Their motion follows the same differential rotation that twists the field below. I note that larger spots tend to appear at lower latitudes, a pattern that repeats every 11 years. This cycle hints at the deeper magnetic choreography, but the exact timing still puzzles us. We don't really know why the magnetic polarity flips precisely after a decade, only that the dynamo must reset somehow. The magnetic pressure inside a flux tube can become comparable to the gas pressure of the surrounding plasma. When that happens, the tube can become buoyant, rising faster than the surrounding flow. I write a quick sketch in the margins. A rising tube, a plume of hot plasma trailing behind, the surface rippling as the tube pierces it. The emergence disturbs the local convection, creating a small whirlpool of motion that can be detected as a Doppler shift in spectral lines. Even as a spot darkens the surface, it also brightens the layers above. The magnetic field guides energetic particles upward, heating the chromosphere and creating bright ribbons that flare briefly. I keep the focus narrow. These are the immediate consequences of the magnetic field breaking through the convective veil. The larger eruptions that launch material into space belong to later chapters. The plasma in the convection zone is not uniform. Its density drops outward, and its temperature falls from millions of degrees at the core to about 6,000 at the surface. This gradient fuels the buoyancy that drives the convective rolls. I find it hard to picture a fluid that is both a gas and a sea of charged particles, moving under its own weight while carrying magnetic fingerprints. The reality feels like a thick, invisible broth, constantly stirred by heat and rotation. Measurements from heliosismology, sound waves that echo inside the sun, give us a picture of the interior flow. Tiny shifts in the wave frequencies tell us where material moves faster or slower. I note that these observations confirm the differential rotation profile and reveal subtle meridional flows that transport magnetic flux toward the poles. The data are noisy, and the inversion process is delicate, but the overall picture aligns with the dynamo model. The sun's magnetic field is not a single, static bar. It is a tangled web that changes on timescales from minutes to years. The convective churn constantly reshapes the field, breaking some loops and knitting others together. I record that the field's energy density in the convection zone is a small fraction of the thermal energy, yet it dominates the dynamics of the outer layers. The paradox that a weak field can control a hot plasma stems from the plasma's high conductivity. When a flux tube reaches the photosphere, the magnetic pressure forces the plasma aside, creating a depression known as a Wilson depression. The surface there sits a few hundred kilometers lower than the surrounding area, a subtle dip that can be measured by precise limb observations. I note that this depression contributes to the darkness of the sunspot, as the cooler, deeper layers become visible. The sun's interior is a place of constant tension between heat, motion, and magnetism. Each component pushes and pulls on the others, producing a delicate balance that sustains the star's output. I sometimes wonder whether the sun ever reaches a truly steady state, or if the churn is an endless adjustment. The answer remains hidden beneath layers we can only probe indirectly. One final observation: the granules we see on the solar surface, tiny, bright cells surrounded by dark lanes, are the tops of the convective rolls. Their size, about 1,000 kilometers across, reflects the depth of the convection zone and the scale at which the plasma can overturn. Watching them evolve, I am reminded that the sun's hidden engine is not a distant, abstract concept, but a living, breathing process that leaves its fingerprint on every flicker of light we receive. I sit at the monitor, the sun's magnetogram scrolling like a restless map. Dark patches cluster where magnetic polarity flips, the so-called active regions. Those spots are where most flares begin, but the surface looks almost calm before anything happens. In an active region, opposite magnetic polarities sit side by side, separated by a thin current sheet. The field lines are stretched, twisted by convective motions beneath the photosphere. Over hours, the stress builds, like a rubber band pulled tighter each minute. The magnetogram shows the shear increasing, the polarity inversion line becoming sharper. At some point, the sheet can no longer hold the tension. The field lines suddenly break and reconnect, a process we call magnetic reconnection. In the reconnection zone, oppositely directed lines snap together and exchange partners. The energy stored in the magnetic field is released as kinetic motion, heat, and particle acceleration. I find it hard to picture how the field lines actually snap. The picture is useful, but the physics is more abstract. The reconnection site is tiny compared to the whole active region, perhaps a few hundred kilometers across. Yet the released energy can be comparable to the output of billions of nuclear bombs. The conversion happens in a few seconds, a rapid cascade that feeds the flare's growth. The plasma is heated to tens of millions of Kelvin, emitting hard that we detect with space-borne instruments. Immediately after reconnection, bright ribbons appear in the chromosphere, flanking the polarity inversion line. Their motion outward marks the footprints of newly reconnected loops. The ribbons are the first flare onset signatures we can see in ultraviolet images. Their speed, often a few tens of kilometers per second, tells us how fast the reconnection front is moving upward. Above the ribbons, a hot, dense loop arcade forms. The loops fill with evaporated chromospheric plasma, a process we call chromospheric evaporation. The upflowing material reaches speeds of several hundred kilometers per second, filling the loops within minutes. The loops then cool, first radiating in soft X-rays, later in extreme ultraviolet. The cooling phase can last from minutes to hours, depending on the loop length and density. Energy release mechanisms are not a single, clean process. Besides reconnection, we see evidence of turbulence in the current sheet, wave dissipation, and shock formation. The accelerated electrons generate Bremsstrahlung, which we record as hard X-ray spikes. Protons and heavier ions are also accelerated, though their signatures are harder to isolate. I don't really know which mechanism dominates in a given flare. The observations often blend together. The timing of these events is surprisingly consistent across many flares. The initial brightening lasts a few seconds, the ribbon separation proceeds for several minutes, and the soft X-ray peak arrives roughly 10 minutes after the hard X-ray burst. The whole episode may linger for an hour before the loops fade away. Yet the exact duration varies, especially when the active region is large or the magnetic shear is extreme. Sometimes a flare is preceded by a small, soft X-ray increase, a pre-flare brightening. We interpret it as a gentle reconfiguration of the magnetic field, a warning that the current sheet is thinning. The pre-flare phase can last from a few minutes to half an hour. It does not guarantee a major flare, but it does show the system is approaching a critical state. Not all reconnection events become flares. Minor reconnection can produce micro-flares or nano-flares, releasing far less energy. The difference lies partly in the amount of magnetic flux involved and partly in the surrounding plasma conditions. We don't really know why some active regions produce only tiny events while others unleash X-class explosions. The answer may be hidden in the three-dimensional geometry of the field, something our line of sight observations cannot fully capture. When a flare reaches the X-class level, the reconnection rate spikes dramatically. The outflow jets from the reconnection region can approach a few thousand kilometers per second. Those jets slam into surrounding plasma, driving termination shocks that further accelerate particles. The shock-accelerated electrons add to the hard X-ray flux, producing the characteristic double peak structure in many high-energy light curves. The magnetic energy conversion is not perfectly efficient. Some of the released energy goes into bulk plasma motion, some into heating, and some into particle acceleration. The partitioning changes from flare to flare, and we can only estimate it by modeling the observed spectra. The models rely on assumptions about the electron distribution, which we cannot measure directly. It doesn't quite make sense when you say it aloud. We infer a lot from indirect signals. Observations from multiple spacecraft give us a three-dimensional view. One satellite may see the ribbons, another captures the hard X-rays, while a third monitors the coronal mass ejection that sometimes follows. Correlating these datasets helps us pin down the sequence of reconnection, particle acceleration, and loop formation. Yet the timing offsets are sometimes a few seconds, enough to blur the causal chain. The flare's magnetic imprint can be seen after the event as a permanent change in the photospheric field. Vector magnetograms show the field becoming more horizontal near the polarity inversion line. This magnetic implosion suggests that the coronal field contracts after releasing its energy. The idea fits the energy budget, but the exact mechanism of the implosion remains debated. Even after the main energy release, the active region may continue to produce smaller bursts, a kind of aftershock. The lingering currents can trigger secondary reconnection sites, creating a cascade of minor brightenings. Those secondary events can last for hours, slowly draining the remaining magnetic stress. In the laboratory, we try to reproduce reconnection with plasma devices, but the scales are vastly different. The solar corona is low density, high temperature, and magnetically dominated, conditions hard to match on Earth. Still, the basic physics, field line breaking, particle acceleration, appears in both settings, giving us confidence that our models capture something real. The final picture is a chain. Convective motions twist magnetic fields, shear builds, a current sheet thins, reconnection ignites, energy cascades into heat and particles, ribbons spread, loops fill, and the system relaxes. Each link is observed, measured, and sometimes missed. The chain is not always smooth. It can snap abruptly or fizzle out. One quiet observation remains. The bright ribbon traced a path about 3,000 kilometers across the solar surface, its edge defined by a sudden increase in ultraviolet intensity. That line, fleeting yet precise, marks the moment magnetic energy turned into light. The GOES satellites have been watching the sun for decades, recording its X-ray output in a steady stream. I stare at those light curves and wonder how a handful of numbers can stand for something as chaotic as a flare. The classification system is simple on paper: A, B, C, M, and X, each letter representing a 10-fold jump in peak flux. A class flares barely rise above the background. A B class is a whisper louder, yet still modest. C class events sit in the middle, releasing about 10 to 10 watts per square meter at Earth's orbit. They happen several times a day during the active phase of the sun, enough to keep the data analysts busy. M-class flares are the workhorses of space weather warnings. Their peak flux lands between 10 and 10 watts per square meter, and they appear roughly once a week at solar maximum. X-class eruptions are the outliers, the rare fireworks that make headlines. Their flux exceeds 10 watts per square meter, and they may linger for hours, dumping energy comparable to billions of nuclear bombs. Energy ranges are expressed in the same units, but the numbers hide a lot of physics. A C-class flare might release 1024 joules, while an X-class can top 1026 joules, a difference of 100-fold. The frequency curve drops steeply as you climb the ladder. In a typical solar cycle, you might count a few hundred C flares, a few dozen M flares, and perhaps a handful of X flares. The rarest, X-class events above X10 appear maybe once in a decade. Historical records give us a sense of the extremes. The 1972 August 4 flare, labeled X20, still sits near the top of the GOES archive. I find it hard to picture the magnetic stress that must have built up before that burst. In 2003, the so-called Halloween storms produced several X-class flares, the largest being X28, which saturated the detectors. The instruments could not record higher values, so we only know it was at least that strong. More recently, in September 2017, an X9.3 flare erupted from a modest sunspot group, reminding us that size alone does not dictate power. The flare's X-ray signature spiked for over 10 minutes, a long tail for an X-class event. The GOES classification is based on the peak 1.8 A-ring X-ray flux measured near Earth, not on the total energy released. That distinction matters when we compare two flares that peak differently but last for different durations. Space weather models often start with the class label because it gives a quick estimate of potential impact. An X-class flare can drive a coronal mass ejection that reaches Earth in a day or two, compressing the magnetosphere. M-class flares can still cause radio blackouts on the sunlit side of the planet, disrupting high-frequency communications. C-class events usually go unnoticed by most users, but they can perturb satellite charging if the background conditions are already tense. The classification does not capture the geometry of the magnetic reconnection. Two X-class flares may differ in how they direct energetic particles, yet both receive the same label. We don't really know how much that geometry matters for the downstream effects. When a flare is recorded, the GOES team assigns a decimal subclass to indicate finer gradations, X 1.2, M 5.4, and so on. Those numbers help forecasters refine the expected X-ray flux, but they still sit within the broader letter bucket. The flare's soft X-ray light curve often shows a rapid rise followed by a slower decay, the classic impulsive phase then gradual phase pattern. I sometimes hear colleagues describe that shape as a fingerprint, yet the fingerprint varies wildly. Frequency statistics come from the Sun's roughly 11-year cycle. During solar minimum, C-class flares may be scarce, while at maximum they dominate the daily count. X-class flares, however, cluster around the peaks of the cycle but are never guaranteed. A quiet sun can still surprise us. In 2009, during an unusually deep minimum, a modest C-class flare was recorded, reminding us that the sun never truly rests. It doesn't quite make sense when you say the sun is quiet and then see a flare appear out of nowhere. The classification system has been in use since the 1970s, when the first GOES X-ray sensors were launched. Over the decades, the detectors have been upgraded, but the letter scheme has endured because it is easy to communicate. Some researchers propose adding a new Super X tier for flares above X10, but the current practice simply adds a higher decimal, like X30. The community has not reached consensus, perhaps because the sample size is tiny. Implications for space weather are immediate. An X-class flare can ionize the upper atmosphere, increasing the density at satellite altitudes and causing orbital decay. I have watched the drag coefficient rise in real time during a recent event. Radio blackouts are classified on a separate scale, but they correlate with the X-ray class. An X-class flare can produce a sudden ionospheric disturbance that knocks out HF communications for hours. That is why the classification matters beyond academic interest. The geomagnetic storm potential also depends on whether the flare is accompanied by a fast coronal mass ejection. Not every X-class flare launches a CME, and not every CME follows an X-class flare. We sometimes overinterpret the class as a guarantee of impact. In practice, forecasters combine the GOES class with solar disk observations, magnetograms, and coronagraph images to assess risk. The flare label is a first clue, a quick shorthand before the deeper analysis begins. When we look back at the most extreme events, the pattern is not always clear. The 1859 Carrington flare, inferred from geomagnetic records, would likely be classified as X30 or higher, yet we have no direct X-ray measurement. I find it hard to reconcile the historical description with modern categories. Modern instruments can capture the flare's hard X-ray and gamma-ray signatures, but the GOES classification remains the backbone of the alert system. The simplicity of a single number makes it possible to broadcast warnings worldwide within seconds. The class also informs the design of spacecraft shielding. Engineers use the worst-case X-class scenario to size radiation hardening, accepting that a rarer, more powerful flare could exceed those limits. It's a compromise between probability and protection. Statistical studies show that the probability of an X-class flare in any given day during solar maximum is roughly 0.1, while a C-class flare is near certainty. That disparity shapes how we allocate monitoring resources. Even within a class, there is variation in the flare's duration. Some X-class flares peak sharply and fade within minutes. Others linger, maintaining high flux for over an hour. Those long-lasting events tend to have more pronounced space weather consequences. The GOES classification does not account for the flare's location on the solar disk. A flare near the limb may be less geoeffective than one near the central meridian, even if both are X-class. That is a subtlety that the label alone cannot convey. When a flare is observed, the data are uploaded to the Space Weather Prediction Center, where the class is added to a public feed. I have watched that feed tick over, each entry a tiny reminder of the sun's restless nature. In the end, the classification is a tool, not a complete description. It gives us a way to sort the endless stream of solar activity into manageable categories. It also forces us to admit the limits of what a single number can tell us. One quiet observation often escapes the headlines. The background X-ray flux, even when no flare is present, fluctuates with the sun's magnetic network. Those subtle variations set the stage for the next burst, a reminder that the sun's mood is never static. The next time a C-class flare flickers across the detector, it may seem insignificant, yet it is part of the same magnetic dance that produces the rare X-class fireworks. I sometimes wonder whether the small flares are merely the aftershocks of larger, hidden stresses. A final note: the GOES X-ray sensor records data in 1-second intervals, producing a grainy but continuous record of the sun's output. Looking at a single second of an X-class flare, the detector's needle jumps, then settles, as if startled by a sudden flash of light. The flare erupts, a sudden brightening that feels like a flash of static across the sun's surface. Inside the tangled magnetic loops, electrons are jerked to near light speed, colliding with dense plasma. Their sudden deceleration produces hard, that we detect as a brief, sharp spike on our instruments. Hard X-rays are only the beginning. A fraction of the accelerated particles reach energies high enough to emit gamma rays when they smash into heavier ions. Those photons carry away a tiny fraction of the flare's total power, but they tell us where the most violent collisions occur. I find it hard to picture the exact geometry of those collisions. Our detectors only see a blurred imprint, not the precise dance of nuclei. Beyond the immediate burst, a cloud of solar energetic particles, SEPs, is launched outward. Protons, helium nuclei, and a sprinkling of heavier ions stream away, carried by the magnetic field that has just reconfigured. Their energies range from a few mega-electronvolts to several giga-electronvolts, enough to punch through the thin atmosphere of a spacecraft. The particle flux can rise by orders of magnitude within minutes, a sudden pressure that feels like a gust of wind in the otherwise empty heliosphere. The SEP population is not uniform. Early on, the most energetic ions arrive first, followed by a slower tail of lower energy particles. This temporal spread mirrors the way a stone dropped in a pond creates concentric ripples that travel at different speeds. We measure the arrival times with particle detectors on board distant probes, and the data look like a staircase, steep steps that gradually level off. A coronal mass ejection, CME, often accompanies the flare, though not every flare throws a CME into space. When a CME does appear, it can act like a magnetic conveyor belt, sweeping up SEPs and guiding them farther into interplanetary space. The CME's shock front can also accelerate particles anew, adding a second, sometimes dominant, component to the SEP event. I sometimes wonder whether the flare-driven particles or the CME-driven particles dominate the radiation hazard at Earth. Our models still wrestle with that question. As the particles travel, they follow the interplanetary magnetic field, a spiraling structure shaped by the sun's rotation. The field lines are like stretched rubber bands, curving outward and winding around the sun. SCPs slide along these bands, occasionally scattering off small irregularities that act like potholes on a road. Each scattering event changes the particle's direction and delays its arrival, making the propagation a bit like a drunkard's walk through a dark hallway. The heliosphere itself is not empty. It contains a tenuous plasma that can dampen the particle stream. When a high-energy proton encounters this background, it may lose a little energy through Coulomb collisions, but the effect is modest compared to the magnetic scattering. The net result is a gradual softening of the spectrum as the particles spread across larger volumes of space. When the SCP flux reaches a planet, its magnetic field becomes the first line of defense. Earth's magnetosphere deflects many of the lower energy particles, funneling the remainder toward the polar regions. There, the particles spiral down magnetic field lines and slam into the upper atmosphere, creating auroral displays that we can see from the ground. The same process occurs at other magnetized worlds, each with its own field geometry and atmospheric composition, shaping the final pattern of energy deposition. The interaction with a planetary magnetic field also induces currents in the planet's conductive layers. In the case of Earth, these currents can flow through power grids and pipelines, sometimes causing measurable voltage spikes. The induced electric field feels like a subtle tug on a loose wire, invisible but potentially disruptive. We monitor these effects with ground-based magnetometers, which record the minute wiggles that betray an incoming SCP storm. Our ability to predict SCP arrival times rests on models that treat the particles as a fluid moving along the magnetic field. Those models must incorporate the solar wind speed, the field line curvature, and the level of turbulence. Yet, turbulence is notoriously hard to quantify. It behaves like a restless sea that changes its character on timescales shorter than our observations. We don't really know how to capture that variability in a single equation, so predictions carry sizable uncertainties. Instrumentation on spacecraft such as the Parker Solar Probe and Solar Orbiter offers a closer look at the acceleration region. Their particle detectors sample the SCP distribution just a few solar radii from the Sun, where the magnetic field is still strong and the plasma is dense. The measurements show that the particle spectra can be very steep, indicating that most particles never reach the highest energies. That steepness fades as the particles travel outward, suggesting ongoing acceleration at the CME shock. Hard X-ray and gamma-ray observations from space-borne telescopes complement the particle data. When a flare produces a strong gamma-ray line, it signals that heavy ions are being accelerated and are colliding with ambient nuclei. Those lines are like fingerprints, each one pointing to a specific reaction. By matching the line intensities with the SCP composition measured later, we can trace the lineage of the particles from Sun to spacecraft. Occasionally, a flare releases a burst of neutrons that escape the Sun without feeling the magnetic field. Those neutrons decay into protons, electrons, and antineutrinos as they travel. The resulting protons join the SCP population, adding a small but detectable component to the overall flux. Detecting those neutrons requires specialized instruments that can differentiate between charged particles and neutral radiation, a technical challenge that still limits our data set. The final leg of the particle's journey is a quiet drift through interplanetary space, a slow glide that can last days. During that drift, the particles lose a little energy to the background plasma, but they retain enough momentum to pose a radiation hazard to astronauts beyond low Earth orbit. The radiation dose feels like a slow, steady drizzle compared to the sudden spike of a solar flare, yet its cumulative effect can be significant over a long mission. One detail that keeps resurfacing in our data is the slight anisotropy in the particle arrival direction during the early phase of an event. The particles tend to come from a narrow cone aligned with the magnetic field line that connects the Sun to the observer. That anisotropy fades as scattering spreads the particles more uniformly. It's a subtle clue that the magnetic connection at the moment of release matters a great deal, even if we cannot resolve the exact field line geometry. The last thing I notice, before the instruments go quiet, is a faint ripple in the magnetic field recorded by a distant probe, an almost imperceptible wiggle that coincides with the tail end of the SCP burst. It's the kind of detail that feels like a whisper of the Sun's restless heart, lingering long after the bright flare has faded. Solar flares launch a brief, intense packet of high-energy photons toward Earth, and the first thing we notice is a sudden loss of HF radio chatter. The ionosphere, that thin shell of charged gas high above us, becomes flooded with electrons, and the ordinary reflection of radio waves collapses, what pilots and mariners call a radio blackout. When the flare's X-rays strike, the D layer of the ionosphere thickens within minutes, absorbing frequencies that normally travel long distances. I find it hard to picture how a few seconds of extra ionization can silence a whole network of emergency communications. The same burst also nudges the upper atmosphere, heating it by a few degrees. That heating makes the atmosphere expand ever so slightly, raising the drag on low Earth orbit satellites. A satellite that usually circles at 400 km may feel an extra millimeter per second of deceleration, enough to shorten its orbital lifetime by weeks if the event repeats. We watch that drag in real time with laser ranging stations that ping the craft and record the return time. The data show a subtle but measurable change in orbital period after a strong flare. It is a reminder that space is not empty. Even a thin veil of gas can push on our machines. Beyond the drag, the energetic particles that follow the flare can penetrate deeper into the magnetosphere. When they encounter the Earth's magnetic field, they spiral along field lines and dump energy into the ionosphere. This creates localized pockets of heightened ionization, which in turn distort the phase of GPS signals. A surveyor trying to map a construction site may see his coordinates jitter by several meters for a few minutes. Power grids feel the flare's echo in a different way. The sudden change in ionospheric currents induces electric fields in the Earth's crust, which drive geomagnetically induced currents, GICs, through long conductors. Transformers, designed for steady currents, can overheat when those stray currents add up. In 1989, a severe storm knocked out a large portion of a northern grid. The chain reaction began with a flare-driven disturbance in the ionosphere. Our monitoring networks try to catch the flare before it reaches us. Space-based observatories watch the Sun in X-ray and extreme UV bands, issuing alerts the moment the flux exceeds a threshold. Those alerts travel through dedicated data links to ground stations that automatically adjust satellite drag models and warn power operators. The warning chain is not instantaneous, though. The spacecraft that detect the flare sit at the L1 Lagrange point, about 1.5 million kilometers sunward of Earth. The photons arrive in 8 minutes. The energetic particles may take hours. In that window, radio blackouts can already be in progress, while the grid still waits for a GIC forecast. Our early warning systems therefore combine several data streams: solar X-ray flux, proton measurements, and ground-based magnetometers that sense the first tremor of a geomagnetic storm. The fusion of those inputs produces a probability map for where the ionosphere will be most disturbed. Operators can then decide whether to shed load, reconfigure satellite orbits, or switch to backup communication bands. Even with the best models, there is uncertainty. The ionosphere is a chaotic medium, and a modest flare can sometimes trigger a larger response than a bigger one. I don't really know why the same solar event can produce a quiet ionosphere on one day and a noisy one on another. Satellite drag predictions illustrate that uncertainty. A drag model may predict a 2% increase in orbital decay, but the actual measurement could be 0.5% or 4%, depending on the thermospheric temperature at the time. Engineers therefore keep a safety margin in their fuel budgets, accepting that a flare could force a maneuver earlier than planned. Power grid operators face a similar dilemma. They must balance the cost of preemptive load shedding against the risk of transformer damage. A false alarm can inconvenience thousands of customers. A missed alarm can burn a transformer beyond repair. The decision rests on a risk estimate that includes the flare's class, the current geomagnetic activity, and the grid's susceptibility. Atmospheric ionization also affects shortwave radio used by amateur operators and emergency services. The ionosphere's reflective properties change rapidly, causing signal strength to swing from clear to mute in seconds. Listeners sometimes report a sudden crack as the wave passes through a newly formed ionized layer. We monitor those changes with ionosondes, vertical radio pulses that bounce off the ionosphere and return a profile of electron density. The trace on the screen jumps up when a flare hits, then settles back over the next hour. The pattern is a useful diagnostic, but it does not tell us the exact impact on a specific communication link. The cascade from flare to ground is a chain of cause and effect, each link measured by a different instrument. A solar X-ray detector logs a spike, a magnetometer records a subtle shift, a power grid sensor notes a fraction of a % voltage sag. Together, they form a picture of the flare's immediate footprint on our technology. Even the most sophisticated early warning network cannot eliminate the need for human judgment. Operators watch the alerts, compare them with local conditions, and decide whether to act. The process feels a bit like watching a weather forecast and then stepping outside with an umbrella, unsure if the rain will be a drizzle or a downpour. Sometimes the flare's impact is so brief that it goes unnoticed by the public. A short-lived radio blackout may affect a single flight's navigation system for a few minutes. Then the system recovers, and the incident is logged as a minor glitch. The event is still recorded in the database, contributing to the statistical understanding of flare impacts. Other times the effect is dramatic enough to make headlines. A sudden loss of satellite coverage can interrupt banking transactions, and a GIC-induced transformer failure can leave a city in darkness for hours. Those moments remind us that the sun, though distant, is an active participant in our daily infrastructure. Our research continues to refine the relationship between flare intensity and each of these impacts. New satellite missions measure the solar wind's composition with greater precision, while ground-based arrays track ionospheric currents in real time. The data feed into models that aim to predict, not just react to, the flare's arrival. Nevertheless, there are limits to what we can forecast. The exact timing of particle arrival depends on the magnetic field's configuration, which can shift in ways we cannot yet predict. I sometimes wonder whether a better grasp of that configuration would let us issue a truly precise warning. Even the best models treat the ionosphere as a set of layers with average densities, but the real atmosphere is full of small-scale irregularities. Those irregularities can scatter radio waves in unexpected directions, creating brief fades that are hard to anticipate. The phenomenon is well known to radio engineers, yet it remains a source of occasional surprise. Early warning networks also have to contend with data latency. A satellite may detect a flare, but the telemetry has to travel through a series of ground stations before reaching the forecasting center. In that interval, the flare's X-ray flux may have already peaked. The warning, therefore, is often a post-event alert rather than a true preemptive notice. Despite those constraints, the system works well enough to prevent the worst outcomes. In the past decade, power grid operators have reported fewer transformer failures during geomagnetic storms, attributing the improvement to better monitoring and timely load shedding. The trend suggests that our collective vigilance does make a difference. The atmosphere's response to a flare can also be felt on the ground in a more subtle way. A sudden increase in ionization raises the conductivity of the air near the surface, which can affect the propagation of very low frequency, VLF, signals used for submarine communication. Those signals sometimes show a brief attenuation that matches the flare's timeline. Scientists use that attenuation as another proxy for ionospheric disturbance, adding yet another data point to the overall picture. The VLF receivers are modest devices, often installed at remote research stations, but they contribute to the global monitoring effort. When a flare is classified as X-class, the alerts become more urgent. The X-ray flux exceeds a certain threshold, and the probability of a radio blackout and increased satellite drag rises sharply. Operators then move to contingency plans, switching to backup frequencies, adjusting satellite attitude, and preparing emergency generators. Even a modest C-class flare can cause measurable effects, especially when the ionosphere is already disturbed by prior activity. The cumulative effect can be more important than any single flare, a fact that sometimes catches planners off guard. Our monitoring networks are expanding, adding new sensors on the ground and in space. A recent addition is a constellation of small CubeSats that measure the upper atmosphere's density directly, providing near real-time drag estimates for satellite operators. The data are streamed to a central hub that fuses them with solar observations. The hub also distributes alerts to power grid control centers, which have automated scripts that can isolate vulnerable sections of the network at the first sign of a GIC. The automation reduces the response time from minutes to seconds, a crucial improvement when the induced currents can rise quickly. Yet automation cannot replace human oversight. Operators still need to verify that an alert is genuine and decide how far to go with protective actions. A false positive can cause unnecessary shutdowns, which in turn may have economic consequences. In practice, the decision chain looks like this. A solar observatory detects a spike, the warning system flags the event. A regional monitoring center checks local geomagnetic conditions, and then the grid operator decides whether to shed load. Each step adds a small delay, but also a layer of verification. The chain works best when each link communicates clearly. Miscommunication can lead to a missed warning, as happened during a moderate flare that produced a brief radio blackout on a transatlantic flight. The pilot reported loss of HF communications, but the ground station had not yet received the flare alert. Such incidents remind us that the timing of information flow is as important as the data itself. A flare's photons travel at light speed, but our awareness of them can lag behind. Reducing that lag remains a key goal for the community. One promising approach is to use machine learning algorithms that ingest solar images and predict flare onset before the X-ray flux peaks. Early prototypes have shown modest success, but they still produce false alarms that would erode trust if deployed widely. I don't really know whether the trade-off will ever be acceptable for critical infrastructure. Meanwhile, the more conventional approach, continuous observation and rapid dissemination continues to serve us. Ground-based magnetometers, space-borne X-ray detectors, and ionospheric sounders all feed into a network that updates every few minutes. Operators have grown accustomed to checking that feed as part of their daily routine. The reality is that solar flares are a reminder that our technology is coupled to a star's activity. The coupling is not a one-way street. Our instruments also provide feedback that helps solar physicists refine their models of flare generation. The data flow is a loop that tightens with each event. On a quiet evening, when the sun is low on the horizon and no flare is imminent, the ionosphere settles into a calm state. The radio waves travel smoothly, satellites glide with predictable drag, and the power grid hums without disturbance. It is a fleeting equilibrium, easily tipped by a sudden burst of solar energy. If you look up at the night sky just after a flare, you might see a faint auroral glow near the poles, though that belongs to another chapter. What you can see from the ground is the subtle shift in a radio receiver's needle, the tiny change in a satellite's orbital period, or the slight dip in voltage at a transformer. Those are the immediate fingerprints of a solar flare, written in the language of our machines. I once watched a ground-based VLF receiver flicker as a flare's X-rays arrived, and the trace lingered a fraction of a second longer than usual. That lingering pulse, barely perceptible, reminded me that even the smallest detail can carry the imprint of a distant explosion. The magnetosphere feels like a stretched rubber band, anchored at the equator and pulled tailward by the solar wind. When the wind presses against the field, a boundary forms, the magnetopause, where magnetic pressure balances the stream of charged particles. I have measured that this surface sits roughly 10 Earth radii sunward on a quiet day, yet it can collapse inward by a few radii during an intense solar storm. The exact shape is hard to pin down. It ripples, bulges, and sometimes folds back on itself like a loose sheet of paper. Inside that invisible shell, the field lines curve back toward the planet, creating two toroidal zones where trapped particles linger. These are the Van Allen radiation belts, first identified by early satellite data. The inner belt holds protons with energies up to hundreds of MeV, while the outer belt is dominated by electrons that can reach relativistic speeds. Their population is not static. During geomagnetic activity, the belts swell, then slowly decay as particles drift and are lost to the atmosphere. I often wonder how the belts maintain their coherence when the surrounding field is constantly being reshaped. Beyond the belts, the field lines stretch far into space, forming the magnetotail. At the far end, opposite the sun, oppositely directed field lines are forced together, creating a thin current sheet. Occasionally, magnetic reconnection occurs there, a sudden rearrangement that snaps the lines into new configurations. The process releases stored magnetic energy and accelerates particles earthward. In my notes, I recorded a burst of energetic electrons that arrived at the inner magnetosphere within minutes after a reconnection event. The timing suggests a direct pathway, but the exact mechanism of particle injection remains only partly understood. Near the poles, the field opens a narrow corridor called the polar cusp. Here the magnetopause dips down, allowing solar wind plasma to spill directly into the upper atmosphere. I have observed that the cusp is not a smooth funnel. It is riddled with small-scale turbulence that mixes solar and terrestrial particles. The density spikes we see in satellite data are fleeting, lasting seconds before the flow is diverted along the field lines toward the auroral oval. The cusp acts like a pressure valve, relieving excess solar wind pressure while feeding the system with fresh particles. Those particles that travel along the field lines eventually encounter the dense layers of the ionosphere. As they descend, they collide with oxygen and nitrogen atoms, transferring energy that excites the atmospheric gases. When the excited atoms relax, they emit photons, the familiar green, red, and violet curtains that we call auroras. The precipitation is not uniform. It concentrates along the auroral oval, a ring that mirrors the shape of the magnetic field at high latitudes. My measurements show that during quiet times the oval is thin, but during substorms it widens, allowing a broader swath of the sky to glow. The magnetosphere's ability to deflect most solar particles rests on the rigidity of its field. Charged particles gyrate around field lines, feeling a Lorentz force that pushes them sideways. This motion creates a drift that carries them around the planet rather than into it. Yet the field is not an impenetrable wall. Its geometry funnels a fraction of the solar wind toward the poles. The balance between deflection and guiding is delicate. When the solar wind pressure rises, the magnetopause compresses and the cusp widens, allowing more particles to enter. Conversely, when the wind eases, the cusp narrows and the belts repopulate. I have tried to model the field using a simple dipole approximation, then added a tail current to reproduce the stretched shape. The model reproduces the overall size of the magnetopause, but it fails to capture the fine structure of the cusp and the rapid onset of reconnection. It doesn't quite make sense when you say it aloud. A smooth dipole cannot generate the jagged edges we observe. This discrepancy reminds me that the real magnetosphere is a living system, constantly reshaped by external pressure and internal currents. Satellite observations provide snapshots of the magnetic field at various points, but stitching them together into a coherent picture is challenging. The Themis mission, for example, placed several probes along the tail to catch reconnection in action. Their data show sudden reversals in the magnetic field direction, accompanied by bursts of high-energy electrons. The timing of these bursts matches the arrival of auroral brightenings in the polar regions, suggesting a causal link. Yet the exact chain of events, from reconnection to particle acceleration to auroral precipitation, still contains gaps. We don't really know how often small-scale reconnection events contribute to the overall energy budget of the aurora. Ground-based magnetometers record subtle variations in the Earth's magnetic field, known as geomagnetic pulsations. These oscillations can be traced back to waves propagating through the magnetosphere, often excited by solar wind fluctuations at the magnetopause. The waves can scatter particles in the radiation belts, causing them to lose energy and precipitate into the atmosphere. In my lab notes, I marked a period when a sudden increase in solar wind pressure coincided with a burst of pulsations and a modest auroral flare. The correlation is clear, but causation is harder to prove. One practical consequence of the magnetosphere's shielding is its protection of satellites and power grids. When the field is compressed, energetic particles can penetrate deeper, increasing the risk of damage to electronic components. The polar cusp, in particular, channels particles into low-altitude orbits, where they can cause single-event upsets. Engineers therefore monitor space weather and adjust satellite operations during periods of heightened activity. My own role is limited to describing the physics, but the chain from solar wind to ground-level effects is a reminder that the magnetosphere is not just a scientific curiosity. Even after decades of observation, the magnetosphere retains an element of mystery. The exact shape of the magnetopause under varying solar conditions, the microphysics of tail reconnection, and the detailed pathways of particle precipitation all resist full description. I find it hard to picture the three-dimensional structure in my mind. The diagrams on paper flatten a complex, dynamic system into static lines. Still, each new measurement adds a piece to the puzzle, slowly sharpening the image. At the very edge of the cusp, a faint hiss of plasma drifts just above the detector's noise floor. a reminder that even the quietest regions are alive with charged particles, waiting for the next gust of solar wind to stir them. The sun constantly spews a tenuous stream of electrons and protons, a wind that drifts outward at a few hundred kilometers per second. When that flow reaches Earth, most of it is deflected by the planet's magnetic shield, but a fraction finds a narrow corridor that runs along the magnetic field lines toward the poles. Those field-aligned currents act like invisible highways, guiding charged particles from the distant plasma into the upper reaches of the atmosphere. At the top of the ionosphere, roughly 300 kilometers above the surface, the particles encounter a region where the magnetic field begins to converge. The field lines squeeze together, increasing the magnetic pressure and forcing the plasma to accelerate downward. I often picture the particles as a thin spray of sand slipping through a narrowing funnel, speeding up as the opening closes. When the particles finally descend into the denser layers, they begin to collide with the gases that make up the upper atmosphere. Nitrogen and oxygen dominate, each with its own set of electronic states. A high-energy electron may knock an oxygen atom into an excited configuration. The atom later relaxes by emitting a photon of green light. A collision with molecular nitrogen can produce a faint blue-purple glow. The specific color depends on the type of gas, the energy of the incoming particle, and the altitude at which the impact occurs. Altitude matters more than most people realize. Below about 100 kilometers, the atmosphere is too thick. Particles lose their energy in a cascade of heat and sound, never reaching the levels where visible emission is efficient. Between 100 and 200 kilometers, oxygen dominates the picture, giving rise to the familiar green curtains that most observers associate with the aurora. Higher up, above 200 kilometers, nitrogen becomes more important, and the displays shift toward reds and purples. The vertical layering is a direct consequence of how the atmospheric density and composition change with height. The precipitation of particles is not a steady drizzle. It is modulated by the solar cycle, an 11-year rhythm in the sun's magnetic activity. During solar maximum, sunspots multiply and solar flares become more frequent, injecting bursts of energetic particles into the wind. Those bursts can amplify the field-aligned currents, delivering a larger dose of plasma into the ionosphere. Conversely, during solar minimum, the influx is subdued, and the aurora tends to be weaker and more confined to the polar cap. Seasonal effects also leave their imprint. In winter, the polar night creates a colder, denser upper atmosphere on the night side, which can enhance the efficiency of particle collisions. The same magnetic field line may carry the same flux of electrons, but the colder air yields brighter emissions. In summer, the same line may produce a fainter glow because the higher temperature spreads the particles over a larger volume, reducing the collision probability per unit distance. Field-aligned currents themselves are not static. They respond to changes in the solar wind's pressure and magnetic orientation. When the interplanetary magnetic field points southward, it can connect directly with Earth's field, opening a channel that allows more plasma to flow inward. That reconnection event can trigger a sudden increase in particle precipitation, sometimes within minutes. I find it hard to picture how quickly the whole system can rearrange itself, yet satellite measurements show the response is startlingly swift. The precipitation pattern is also shaped by the geometry of the magnetic field. Near the magnetic poles, the field lines are nearly vertical, guiding particles straight down. Further equatorward, the lines tilt, and particles must travel longer distances before they encounter dense enough air to produce light. This explains why auroral ovals expand and contract, sometimes reaching mid-latitudes during strong geomagnetic storms. The oval's shape is a direct map of where the field-aligned currents intersect the ionosphere. Collisions are not purely elastic. They can also ionize the atmospheric constituents, creating secondary electrons that join the precipitation stream. Those secondary electrons can, in turn, excite additional atoms, amplifying the brightness of the display. The cascade can be self-sustaining for a short time, but it quickly runs out of energy as the particles lose momentum. We don't really know how far the cascade can propagate before it stalls, because the measurements are sparse at those altitudes. The auroral emission itself is a quiet reminder of the energy conversion taking place. Kinetic energy carried by a solar particle is transformed into electromagnetic radiation, a process that can be measured in watts per square meter. The total power of a major auroral event can rival the output of a small city, yet it is spread over a vast area, making the local intensity modest. That contrast between global scale and local subtlety is easy to miss when watching the lights from a single viewpoint. Magnetospheric waves sometimes ride along the same field lines, modulating the particle flux. These Ulfvane waves can accelerate electrons locally, adding a burst of energy just before they strike the atmosphere. The timing of such wave-particle interactions is delicate. A wave arriving a few seconds earlier or later can change the color palette of the aurora. I sometimes wonder whether we will ever be able to predict those micro-variations with any certainty. Observations from ground-based imagers and orbiting spectrometers agree on the basic picture, yet each instrument sees only a slice of the whole. Ground stations capture the visual brilliance but miss the high-altitude red emissions that occur above their line of sight. Satellites record the particle flux but cannot resolve the fine structure of the shimmering curtains. The incomplete dataset forces us to stitch together a model that is always a little rough around the edges. Even with all the data, the exact trigger that decides whether a particular field-aligned current will produce a vivid aurora or remain invisible is elusive. Small changes in solar wind density, magnetic shear, or ionospheric conductivity can tip the balance. We have statistical relationships, but the day-to-day variability still feels like a flickering candle in a draft. One concrete detail that keeps resurfacing in the data is the correlation between the intensity of the green line at 557.7 nm and the electron energy around a few key V. When the electron flux peaks near that energy, the green emission spikes, creating the classic curtains that ripple across the night sky. The line is narrow, yet its brightness can fluctuate by orders of magnitude within a single minute. This precise link between particle energy and color remains a useful diagnostic, even as the broader system stays stubbornly complex. The night sky over the polar caps often looks like a restless sheet of paper, torn open by invisible hands. When electrons from the sun plunge along the Earth's magnetic field, they strike the thin upper atmosphere and set off a cascade of light. The colors we see, green, red, purple, are not random. They are fingerprints of the atoms they excite. Oxygen dominates the upper atmosphere at the altitudes where most auroras appear, roughly 100 to 250 kilometers up. When an energetic electron collides with an oxygen atom, it can raise an electron in that atom to a higher energy level. As the excited electron drops back, it releases a photon. If the transition is from the 1s to the 3p state, the photon has a wavelength near 557 nanometers, what we call a vivid green. This green band is the most common auroral color because the transition is efficient and the oxygen density is high at those heights. Higher up, above about 200 kilometers, the same oxygen atoms can be excited to a different state, the 1d level. Their return emits a deep red photon at 630 nanometers. The red glow is fainter because the transition is slower and the atmosphere is thinner there. I find it hard to picture how a handful of atoms, spread over a vast volume, can generate a color that fills the horizon, yet the physics adds up. Nitrogen tells a different story. Molecular nitrogen, N2, and its ionized form, N2+, dominate at lower altitudes, around 80 to 120 kilometers. When electrons knock a nitrogen molecule into an excited state, the molecule can emit a photon in the blue or violet range, typically 427 nanometers. These shorter wavelengths are less visible to the eye, especially when mixed with brighter greens, but under strong activity, they add a subtle purple tint that outlines the main curtains. The energy of the incoming electrons matters a lot. Low-energy electrons, a few hundred electron volts, tend to deposit their energy deeper, where nitrogen is more abundant, giving rise to the bluish-purple shades. Higher energy electrons, several kilo-electron volts, penetrate further, exciting the oxygen that produces green and, at the very top, red. The distribution of electron energies is not uniform. It fluctuates with the solar wind's conditions and the magnetospheric dynamics that guide the particles. Magnetic field lines act as highways for these electrons. Near the poles, the field lines curve sharply toward the Earth, converging at the magnetic footpoints. The geometry of those lines shapes the auroral forms we observe. When a bundle of field lines is relatively smooth, the precipitating electrons follow a narrow channel, and the resulting light appears as a thin, pulsating arc. If the field lines are twisted by magnetospheric waves, the electrons spread out, and the aurora spreads into curtains that ripple like silk. Wave-particle interactions add another layer of complexity. Ulfvane waves, magnetized ripples that travel along field lines, can accelerate electrons locally. When a wave packet encounters a population of electrons, it can transfer energy in a resonant fashion, boosting some electrons to higher energies. Those boosted electrons then light up a new patch of sky, often as a sudden brightening or a flickering filament. I don't really know how often a single wave packet creates a visible filament, but observations suggest it is a common trigger for the rapid pulsations we see. Temporal dynamics are evident in the way auroras pulse, fold, and drift. The magnetosphere is never static. It sways under the pressure of the solar wind. When the wind's magnetic field aligns opposite to Earth's, reconnection events fling bursts of plasma toward the poles. Those bursts arrive as discrete ejections, each lasting a few seconds to minutes. The resulting auroral display can shift from a steady glow to a series of rapid, staccato pulses. The timing of these pulses matches the cadence of the injected electrons, linking the large-scale solar wind to the fine-scale flicker of the sky. Curtains often appear to fold over themselves, forming spirals that seem to rotate. This pattern emerges when the field-aligned currents, electric currents that flow along magnetic field lines, vary in strength along the arc. A stronger current in one segment pulls the plasma faster, stretching the luminous ribbon into a spiral. The curvature of the field lines also contributes. As they dip toward the Earth, the visible arc follows a curved path that can look like a half circle or a full loop, depending on the observer's perspective. Pulsating arcs are another frequent form. They appear as diffuse bands that brighten and dim on a roughly 10-second cycle. The underlying cause is thought to be a modulation of the electron precipitation by ultra-low frequency waves trapped in the magnetosphere. Those waves act like a metronome, periodically opening and closing the gate through which electrons descend. The result is a rhythmic breathing of light that can persist for several minutes. When the aurora is especially intense, the different colors can coexist in a single structure. A green curtain may be outlined by a thin violet edge, while a red halo crowns the top. The layering reflects the vertical stratification of the atmosphere. Nitrogen emissions dominate lower down, oxygen green in the middle, and oxygen red at the highest reaches. The eye integrates these layers, producing a composite hue that can shift as the aurora moves. It is tempting to think of the aurora as a single phenomenon, but the color palette tells a story about altitude, composition, and electron energy. The same magnetic field line can carry electrons of varying energies at the same time, lighting different layers simultaneously. In practice, the observed color mix is a snapshot of many overlapping processes, each with its own timescale. Magnetospheric substorms add yet another twist. During a substorm, the stored magnetic energy in the tail of the magnetosphere is suddenly released. This energy accelerates a large number of electrons earthward, often producing a spectacular expansion of the auroral oval. The sudden influx can push the green emission down to lower altitudes, where the denser air quenches the green photons more quickly, allowing the red line to dominate for a brief interval. The rapid color shift is a hallmark of substorm onset. Even the shape of the aurora can hint at the underlying magnetic topology. A simple east-west arc suggests a relatively uniform field line orientation, while a series of north-south aligned ribbons points to a more complex, possibly twisted field configuration. Spirals and curls often indicate that the field lines are sheared, perhaps by the interaction of the solar wind with the magnetosphere's tail. Wave-particle interactions are not limited to Wolfvane waves. Whistler mode waves, which propagate at higher frequencies, can also scatter electrons into lost cones, directions that lead them into the atmosphere. When such scattering is strong, the resulting aurora can appear as a series of discrete, narrow bands rather than a continuous curtain. The bands may drift apart, reflecting the motion of the underlying wave pattern. Temporal variability is also evident in the way auroras respond to sudden changes in solar wind pressure. A sudden increase, called a pressure pulse, can compress the magnetosphere, shifting the footprints of field lines equatorward. The auroral oval then moves, and the colors can change as the precipitating electrons encounter different atmospheric densities. The shift can happen in less than a minute, a reminder that the whole system reacts on human timescales. I sometimes wonder how much of the observed structure is shaped by the instrument we use to look at it. Human eyes are more sensitive to green than to red or violet, so the green component often dominates our perception. Yet a spectrograph would reveal a richer mixture of lines, each telling its own part of the story. We don't really know how many faint red threads are hidden beneath a bright green curtain because they are simply too dim to register. The aurora's forms are not static, they evolve as the particle precipitation changes. A curtain can break into separate arcs, which then merge again, like a fluid flow that separates and coalesces. This fluid-like behavior arises because the plasma in the ionosphere is partially conductive. Currents can redistribute, reshaping the luminous patterns. The underlying magnetic field remains the scaffold, but the plasma's motion adds a layer of dynamism. Observations from low Earth orbit have shown that the auroral emissions can extend several hundred kilometers along the magnetic field line, forming elongated structures that we see projected onto the sky. When the satellite passes through one of these structures, it measures a burst of energetic electrons that matches the timing of a brightening scene on the ground. The correspondence confirms that the visible forms are direct signatures of particle fluxes along field lines. The color of an aurora can also be affected by collisional quenching. At lower altitudes, where the air is denser, excited oxygen atoms may collide with other particles before they can emit a photon, effectively suppressing the green line. In such cases, the red line, which has a longer lifetime, can survive the collisions and become the dominant color. This quenching explains why some low-altitude auroras appear reddish even when the electron energies would normally favor green. Finally, the subtle variations in hue, like a faint teal edging a bright green, often arise from the superposition of multiple emission lines that are close in wavelength. The human eye blends them, producing a color that is not represented by any single transition. It is a reminder that the aurora is a composite of many microscopic events, each adding its own shade to the whole. As the night drifts on, the sky may settle into a quiet green wash, or it may erupt into a rapid succession of spirals and pulsations. The exact pattern at any moment is the result of a delicate balance between magnetic geometry, particle energy, atmospheric composition, and wave activity. I find it hard to picture all those factors aligning perfectly, yet the aurora does it night after night. A single violet filament, barely a thread against the dark, flickered for a heartbeat before fading into the green background. The aurora that sweeps across polar skies is not a single phenomenon but two mirror-like displays, one over the north, one over the south. Their green and red curtains arise from the same solar particles, yet the places where they can be seen differ because Earth's magnetic field is tilted and offset from the rotational axis. In practice, this means the auroral oval hugs the magnetic poles, stretching farther over the northern hemisphere where the continent reaches higher latitudes, while the southern oval lies over a mostly oceanic expanse. Latitude is the first gatekeeper. Observers below about 55 degrees N rarely catch a glimpse, even during strong storms. Above 70 degrees N, the sky is almost always alive with faint glows, especially when the sun is quiet. In the southern hemisphere, the threshold is similar, but the landmass that sits under the oval is thin. The Antarctic Peninsula, at roughly 65 degrees 70 degrees S, offers the best ground-based views. The rest of the continent is locked beneath thick ice and perpetual cold, making human presence rare. Seasonal darkness adds a second filter. During the Arctic winter, the sun stays below the horizon for months, granting long, uninterrupted nights. That darkness lets even weak auroras be recorded on film or by a simple eye. In summer, the midnight sun blinds the sky, and the same magnetic activity passes unnoticed. The Antarctic follows the same pattern, but the research stations there operate on a schedule that often keeps lights on for safety, which can mask subtle colors. I find it hard to picture a night in the middle of Antarctic summer when the sky is still bright enough to read a map, yet the aurora is trying to paint itself across it. Indigenous peoples have lived under these lights for millennia, and their stories reveal a practical relationship with the flickering sky. The Inuit of Greenland speak of the spirit lights that guide hunters, warning them of strong winds that could capsize kayaks. Their folklore mentions the aurora as the breath of a great polar bear, a reminder that the environment is alive and watchful. Far to the south, the Sami of northern Scandinavia called the lights the fox's tail, believing that a swift animal chased across the snow, scattering sparks into the air. In both cases, the narratives tie the luminous dance to survival, not to abstract wonder. In the southern Pacific, Maori legends describe the aurora as the spear of the god of war, flashing across the southern horizon as a warning of conflict among tribes. Aboriginal Australians of the southern coast, though rarely seeing the aurora directly, recorded it in rock art as a series of jagged lines, perhaps a distant memory of an ancient climate shift that brought the magnetic pole closer to their latitude. These myths, while diverse, share a common thread. The lights are messages, not merely spectacles. Modern tourism has turned those ancient messages into ticketed experiences. In Norway, small towns like Tromsø market, aurora chasing, trips that blend scientific briefings with heated cabins and hot drinks. Guides often quote the KP index, a numeric scale of geomagnetic activity, while pointing out the faint pink band that signals a sub-storm. In Iceland, the road to the West Fjords offers a dark corridor where the sky can be read like a weather map. Even in Antarctica, a handful of expedition vessels now carry passengers to the peninsula during the austral winter, promising a front-row seat to a display most people never see. I sometimes wonder whether the presence of cameras and bright headlights changes the way the aurora is perceived, but the data on that are sparse. The same magnetic storms that paint the sky also mess with the technology that explorers rely on. Early 20th century polar expeditions reported sudden radio blackouts when the aurora surged, a problem that forced them to switch to Morse code lamps or wait out the disturbance. Even today, satellite communications can be degraded by ionospheric turbulence seeded by the same charged particles that create the lights. The effect is strongest near the magnetic pole, so stations on the Arctic coast have to schedule data transfers around predicted auroral activity. We don't really know how future quantum communication links will behave under such conditions, but the pattern repeats: beautiful sky, inconvenient interference. Scientific stations keep detailed logs of auroral intensity, linking them to solar wind measurements taken by orbiting observatories. Those logs often note the auroral footprint on the ground, a faint glow that lingers after the main curtain has faded. In the north, this footprint can be traced across the tundra, lighting up mosses and snow in a soft, emerald hue. In the south, the same effect is seen on the icy shelves of the Ross Ice Shelf, where the reflected light creates a phosphorescent sheen on the surface. The difference is not in physics, but in what the light meets: vegetation versus pure ice. Cultural festivals have sprung up around the predictable peaks of auroral activity. In Finland, the night of the northern lights coincides with the winter solstice, and communities gather around bonfires, singing songs that echo old lullabies about the sky's fire. In Chile's Patagonia, a small town holds an Aurora Australis fair each August, where locals serve hot cocoa infused with native herbs, while scientists give short talks about the solar wind. These gatherings show that the aurora still serves as a focal point for community, a shared experience that bridges scientific curiosity and folk tradition. Even the language we use reflects this duality. In English, Northern Lights feels almost casual, a tourist slogan, whereas Aurora Borealis carries a Latin gravitas that hints at its astronomical roots. The southern counterpart, Aurora Australis, is less common in everyday speech, perhaps because fewer people can claim to have seen it. That linguistic gap mirrors the geographic one. More humans live under the northern oval, so the phenomenon has woven itself tighter into our collective imagination. There are still gaps in our understanding of how the aurora shapes cultural identity. Some scholars argue that the visual intensity of the lights correlates with the richness of myth, but the evidence is anecdotal at best. I find it hard to picture a systematic survey that could separate the influence of climate, isolation, and trade routes from the pure visual impact. Until such work is done, the link remains a compelling hypothesis rather than a proven fact. One practical consequence of the aurora's reach is its effect on navigation. Before the advent of GPS, polar explorers used magnetic compasses that could swing wildly under auroral currents. The resulting errors sometimes forced entire crews to alter routes, adding days to journeys and consuming precious supplies. Modern vessels now carry magnetometers that record these deviations in real time, feeding the data back to research centers that model the ionospheric currents. The feedback loop is subtle. The aurora disrupts navigation, which in turn provides measurements that improve our models of the aurora itself. A final observation comes from a lone researcher stationed on a small island off the coast of Greenland. He noted that on a night when the sky was a deep indigo, a thin, violet ribbon slipped across the horizon for just a few seconds before dissolving. No camera captured it. Only his notebook recorded the fleeting moment. The Aurora, it seems, still holds secrets that slip through our instruments as easily as they slip through our stories. The instruments aboard Solar Orbiter now stare at the Sun from a perch just inside Mercury's orbit, measuring magnetic twists and particle streams that never reach Earth. I watch the data streams like a slow-moving tide, waiting for something that will not always arrive. Parker's solar probe, meanwhile, has already brushed the corona at 9.8 solar radii, sampling plasma that is hotter than a furnace. Its heat-shielded sensors record voltage spikes that feel like the hiss of a distant radio. Both spacecraft send us snapshots of the same magnetic rope from different angles, like two cameras trying to photograph a fleeting firework. The overlap is imperfect, and that is where the real work begins. When the two data sets are overlaid, patterns emerge, tiny bursts of reconnection that precede larger flares by minutes. I find it hard to picture how a knot of field lines can store enough energy to launch a burst that lights up the whole solar disk. The first surprise was that many of those tiny bursts never grew into full-scale flares. They fizzed out, leaving a quiet wake. It doesn't quite make sense when you say it aloud. Why does the Sun sometimes decide to hold back? Ground-based Aurora imagers now form a network stretching from Scandinavia to Antarctica, each camera calibrated to catch the faintest green and red curtains. The images are stitched together in near real time, producing a global map of the nighttime ionosphere. The network's resolution is enough to see individual arcs that flicker on a timescale of seconds. Those arcs often match the arrival of a solar wind packet measured by a spacecraft upstream. The correlation is clear, but the causality remains vague. Machine learning models have been trained on decades of solar wind and geomagnetic indices, learning to predict K-index spikes a few hours in advance. The algorithms are essentially pattern recognizers, not physics solvers. When the model flags a potential storm, operators receive an alert that looks like a simple probability bar. The bar is useful, yet it hides the fact that the underlying data sometimes contradict each other. We don't really know how robust the forecast will be when a truly novel event occurs. One of the open questions that still haunts the community is what exactly triggers the sudden release of magnetic energy in a flare. Some theories point to the slow build-up of shear, others to the emergence of new flux tubes. Observations from Solar Orbiter show that the magnetic shear can reach a critical angle, but the angle alone does not guarantee a flare. I have seen cases where the shear is high and nothing happens, and others where a modest shear erupts violently. Another puzzle is the role of turbulence in the corona. Turbulent eddies could act like a catalyst, nudging a marginally stable configuration over the edge. The data hint at turbulence, but the measurements are too sparse to map it fully. Protecting our technology from solar storms is becoming a practical concern rather than a theoretical curiosity. Satellite operators now receive warnings that include expected flux levels and suggested safe mode procedures. Power grid managers are experimenting with real-time load shedding based on forecasted geomagnetic-induced currents. The idea is simple: reduce the current before the storm hits. In practice, the timing is delicate, and a false alarm can be costly. Future missions aim to fill the gaps that still exist. The European Space Agency plans a follow-up to Solar Orbiter that will carry a high-resolution magnetograph capable of measuring the vector field at the photosphere with unprecedented fidelity. NASA's next proposal includes a constellation of small probes placed at Lagrange points L1, L4, and L5 to sample the solar wind from multiple directions simultaneously. The goal is to capture the three-dimensional structure of an incoming CME before it reaches Earth. A lunar-based Aurora imager has been suggested, taking advantage of the moon's far side to avoid Earth-based light pollution. The instrument would watch the Earth's magnetotail from a stable platform, perhaps catching the first signs of substorm onset. On the ground, the Aurora network is being upgraded with spectrometers that can resolve the fine structure of the 557.7 nm green line. Those spectrometers will tell us how the energy is partitioned among electrons of different energies. In parallel, laboratory plasma experiments are reproducing small-scale reconnection events, allowing us to test theories under controlled conditions. The experiments are noisy, but they provide a tangible link between theory and the space data. The machine learning community is also working on hybrid models that embed physical constraints into the learning algorithm. The hope is to prevent the model from learning spurious correlations that vanish when the sun behaves differently. All of these efforts share a common thread. They try to turn a chaotic, distant process into something we can anticipate and, if necessary, mitigate. The ambition is modest, not heroic. I sometimes wonder whether the sun will ever be fully predictable or whether we will always be chasing a moving target. The answer may lie in a combination of better measurements and better models. One small observation from the latest Aurora night, captured by a Norwegian imager, shows a thin, persistent green ribbon hugging the magnetic equator for over 30 minutes. The ribbon's brightness fluctuated in step, with a low-frequency wave detected by a nearby magnetometer.